All right, everyone, welcome back to Etale Cohomology. So today, the goal is to finish talking about Brauer groups and use what we've learned to compute the cohomology of curves. But before we do that, are there any questions? All right, if not, let's get started. So let me remind you what we did. So last time we discussed the definition of the Brauer group and proved it's a group. And then we interpreted, so given alpha a 2 cocycle in, so representing, so this was a check 2 cocycle representing a class alpha in the Brauer group of X, we learned how to understand it geometrically. So in particular, we discussed a category of alpha twisted sheaves. So briefly, what these were was alpha is a cocycle defined on some cover of X. An alpha twisted sheaf is a sheaf on the cover and kind of twisted descent data. So meaning isomorphisms on the double intersections of our cover, which don't satisfy the cocycle condition, but where their failure to do so is measured by alpha. So this was some kind of very nice category, like an abelian category that looks kind of like quasi-coherent sheaves and is in fact quasi-coherent sheaves if alpha is the constant sheaf 1, there's a constant cocycle 1. And this let us think about two other ways of interpreting a Brauer class, which are maybe more classical, one of which is Savary-Brauer varieties. So Savary-Brauer schemes. So these were twisted forms of projective space, and one goes from a twisted sheaf to a twisted form of projective space by projectivizing it. And 2 was Azumaya algebras. And here we went from E to the projectivization of E, which is at least descent data for a scheme because projectivizing gets rid of the failure of the cocycle condition. And in fact, I argued, at least verbally, that that descent data is effective. And here, to go from a twisted sheaf to an Azumaya algebra, we took the endomorphism algebra of E. So this is a quasi-coherent sheaf of, well, sorry, here, if this is a twisted vector bundle. And given a twisted vector bundle, E, we can take its endomorphism algebra, and this is a coherent sheaf of algebras. There's a bit of noise from someone eating breakfast in the background, so whoever that is, would you mind muting yourself? Thank you. So this NE is a coherent sheaf of algebras. And it, moreover, is an Azumaya algebra, which means étale locally, it's isomorphic to a matrix algebra. Right? In other words, the endomorphisms of a trivial vector bundle. And that's just because a alpha twisted vector bundle is étale locally a vector bundle. Okay, so I want to use this geometric description to prove something. So I want to prove the following theorem, which is sometimes people call it Tsen's theorem or the Tsen-Lang theorem. So it's the following. So suppose that K is a quasi-algebraically closed field. Sorry, K is a C1 field. So what does that mean? Does anyone know what this means? Anyone?
I guess
I'm sorry, Peter?
I guess if you have the degree of polynomials, yes, smaller than the number of variables, and you always have solutions.
Yeah, that's right. So C1 field, okay, so I just checked, actually, I got a little bit confused. So this is the same as a quasi-algebraically closed field. And Peter more or less gave us the definition, which I'll write down here. So we say K is quasi-algebraically closed if for any homogeneous polynomial f in K adjoin x1 through xn with degree of f less than n, so the degree is less than the number of variables. And then what's the condition? So we're given a homogeneous polynomial. A homogeneous polynomial always has a trivial zero, namely set all the variables equal to 0. And we're going to assume that it has a non-trivial zero. Okay, and people also sometimes call this a C1 field. And there's a notion of a Cn field where you require this degree is, instead of being less than n, you require maybe the degree to the n is less than n. Sorry, the degree to the m is less than n. So that's a Cm field. Okay, so what's the theorem? So suppose you have a C1 field. That means that any homogeneous polynomial of low degree has a non-trivial zero, or equivalently a quasi-algebraically closed field. Those are the same thing. Then the theorem is that the Brauer group of K is 0. All right, are there any questions about the statement? So maybe let me move the definition of C1 or quasi-algebraically closed up here. All right, are there any questions about this? Okay, and then we're also going to prove the following theorem. Suppose K is one of the two of the following things. One, the function field of a curve. Over an algebraically closed field. Or two, the fraction field of a strictly Henselian DVR. Then K is quasi-algebraically closed, or C1. Okay, so strictly speaking, I think what I'm going to do is prove 1 and give you a reference for 2, because we're spending a lot of time on this topic. It's a wonderful topic, but I don't want to turn this into a course on Brauer groups. Then the corollary of this is going to be that the Brauer group of K with K as above is trivial. And let me just remind you, so we more or less reduced computing the cohomology of curves with coefficients in GM at least, and hence with coefficients in, let's say, Z mod L to the n or mu n, to the vanishing of some higher cohomology. And this is more or less that vanishing in H2. Right, so there's a couple missing things, which I'll explain once I prove this theorem, but this is at least that H2 vanishing, and then we're going to use that to deduce some higher cohomological vanishing. Okay, are there any questions about the basic strategy or what we're trying to do right now? All right, so I want to start by proving Tsen's theorem, and it's actually very simple with what we've done, but I'm going to need a definition, which is the notion of the reduced norm. So the reduced norm is to Azumai algebras, so endomorphisms of twisted sheaves, what the determinant is to matrix algebras. Okay, and that's actually the definition. So let E be an alpha twisted sheaf. And ND then is an Azumai algebra. So that's just endomorphisms, the endomorphism sheaf of E. Then the reduced norm, which I'll just call norm, and E to, so this is just a multiplicative map to end of the top exterior power of E. Well, what is this? So this is a line bundle. An end of a line bundle is O. Is just given by functoriality. Of wedge. So given an endomorphism, you can take its top exterior power, and that's an endomorphism of the top exterior power of the thing your original thing was an endomorphism of. All right. So this is exactly the determinant if E is a trivial vector bundle. Are there any questions about the definition? Okay, and then the simple proposition is that given an endomorphism of our twisted sheaf, so F in end of E, F is invertible if and only if. So can anyone tell me, how do you check if a matrix is invertible?
Yes, its image in the determinant bundle is non-zero.
It's not just that the determinant is non-zero, so Arvind, what you said is correct over a field. In general, if you're over a ring, a matrix is invertible if its determinant is a unit, right?
Right.
Yeah, so, sorry. So here, this is if the norm of F is a unit. So can anyone prove this proposition for me? So my hint is that invertibility is something you can check locally. Ben, you unmuted?
Yeah, well, I was going to say that, but then locally it's a matrix algebra, and you know that this fact for matrix algebras.
Yeah, exactly right. So we just reduce to the local situation where ND is just a matrix algebra. So the proof is just check locally. Great. So now let's prove Tsen's theorem. So let me remind you what this said. So this said K quasi-algebraically closed. So just a reminder, that means that a homogeneous polynomial of degree n, of degree less than n, has a non-trivial zero. So this implies that that the Bauer group of K is zero. Okay. So so what do we want to show? So we want to show that given an alpha in the Bauer group of K, we can find an alpha twisted line bundle. So maybe it's a little bit silly to be talking about twisted sheaves on spec K, but I think it's sort of a useful point of view. So we'll see what happens. Okay, so what do we have? So we want an alpha twisted line bundle. What we have is some alpha twisted vector bundle, E. So why is that? That's just what it means to be in the Bauer group. Okay, so anyone have any suggestions? And my hint is that we're going to use the reduced norm. So what do we want to do? Well, if E has rank 1, we're done, right? So what we want to do is we want to find a subbundle or a quotient bundle of lower rank. And so the idea is to find a non-trivial subbundle of E if the rank of E is bigger than 1. And if we can do that, we win, right? Because then we can keep going until we get something of rank 1. Does everyone agree that the strategy sounds plausible? Or does anyone disagree, maybe is a better question? All right, I will take your silence as assent. Cool. So, okay, so how do we do that? Well, maybe one thing we could try would be to find an endomorphism of E with non-trivial kernel or co-kernel, right? And since we're over a field, any quotient or sub of a vector bundle is a vector bundle, right? It has constant rank because there's only one place for it. You have to check the rank. Okay, so we're gonna find F in ND. So this is our, as my algebra, or since we're over a field, essential simple algebra, which is not invertible. And we just said what that means. That just means that the norm of F, the reduced norm, is 0. So being invertible means that, that the norm is a unit, we're over a field. So the only way you cannot be a unit is if you're 0, as Arvin said earlier. All right, can anyone help me do this? So somehow we have to use the hypothesis, right, that K is quasi-algebraically closed. So how are we going to do that?
So you should show that the degree of this norm thing is somehow bigger than the number of variables.
Great, yeah, that's exactly right. So let's think about this. So norm here is a function. It's a polynomial function from n to e to k, right? So this is just a rank of e squared dimensional affine space. So in other words, the norm, that means that norm is a polynomial function in rank of e squared variables. Okay, to actually check this rigorously, what you would do is extend k so that nd splits, and then norm just becomes the determinant. So what's the same argument tells us the degree of our norm function. So what's the degree of norm? Anyone?
Probably rank of E.
Yeah, it's just rank of E, and we can just check that again by passing to a finite extension where norm just becomes the determinant, and the determinant has degree n if you have an n by n matrix, right? It's degree n in the entries of that matrix. So that means that, so this was step 1 maybe. So we've now found, now we're going to argue, well, we have this function, it's homogeneous, right? Because the determinant is homogeneous. It's in rank e squared variables, and it's rank e. So this means that quasi-algebraically closed implies that norm has a non-trivial 0. If the rank is bigger than 1. And we need rank bigger than 1 because we need the degree to be less than the number of variables. So rank e needs to be less than rank e squared. So in other words, there exists f in nd, which is non-zero. So quasi-algebraic closedness gives us a non-trivial 0, such that norm of f equals 0. Are you guys with me so far?
Yes.
Great. Okay, and now what we can do is we can set E prime, for example, to be the kernel of F. And this is an alpha twisted vector bundle of rank less than the rank of E. Okay, and now we're done. Our original idea says, well, now that says that as long as we have rank at least 1, we can find a subbundle of lower rank and keep going until we get to a line bundle. And then we said earlier last time that having an alpha twisted line bundle implied alpha was the trivial Brouwer class. So maybe let me write that. So keep going until you find something, and then you're done. So once you have an alpha twisted line bundle, this implies that the class of alpha is 0 in Brouwer. Great. Are there any questions about that? Okay, and there's a corollary of this, which is what we're actually going to use, but I'm not going to prove, which is that if K is a quasi-algebraically closed field, then H2 of K with coefficients in GM is equal to 0. Okay, and the proof is not trivial, but it's sort of field theory, so I don't want to give it here. The proof is that for a field, the H2 of GM equals the Brouwer group of K. So a priori, the Brouwer group is just a subset, but in fact, for fields, they're equal. And in fact, they're equal in much more generality than that. So the remark, which is maybe worth making, is that this is true, not in general, but in a lot of situations. So I think, for example, for like regular rings, I think it's true, for example. But and it's not true for schemes in general. But it's hard to make a counterexample. Yeah. So what's true in very wide generality is that the Brouwer group is equal to the cohomological Brouwer group. So that's not true for all schemes, but I think it's true, for example, for all affine or maybe quasi-affine schemes. Maybe even weaker conditions than that. Maybe all you need is like quasi-separated. I would have to check. Maybe quasi-compact and quasi-separated. So Dauber has a very strong result along these lines. But for fields, it's not very hard. And the proof for fields is you just write down an explicit central simple algebra using a cocycle. So you have to show that every cocycle gets hit by some central simple algebra, and you just write one down. And this is in Serre's local fields, for example. Okay, so we've now, assuming we can produce some quasi-algebraically closed fields, we've now produced some examples of fields with trivial Brouwer group. So now I want to give you a proof that of the following. That certain fields are actually quasi-algebraically closed. So the key example where I'm going to give you a proof is if K is K of C, which is the function field of a curve, over an algebraically closed field, I'm going to prove that this is quasi-algebraically closed. So in particular, combining this with the corollary above, we'll see that the H2 of such a field, so H2 of the function field of a curve with coefficients in GM is 0. And the Weil divisor exact, sorry, the divisor exact sequence we discussed a couple class periods ago told us that that group was closely related to the Etale homology of a curve. All right. Are there any questions before I start giving this proof? All right, so what do we want? So given a function f in K of C, adjoint x1 through xn, which is homogeneous, and such that the degree of f is less than n, we want to produce a non-trivial 0 of f in K adjoins C to the n. So non-trivial just means that not all the entries are 0. All right. And in fact, we're going to get this from the Riemann-Roch theorem. So what's the idea? Well, actually, I'm curious. Does anyone have any ideas? Who hasn't, or has anyone seen this proof before? I think it's a really amazing idea. So what we're going to do is we're going to study functions on C. So the subset of K of C consisting of functions with bounded poles. So in other words, sections to line bundles on C. So we're going to choose an ample divisor D on C. And we're going to consider f as a function on the global sections of C with coefficients in O of MD. All right, so can anyone tell me where this lands? So suppose I plug in some, so what was this global sections of C with coefficients in O of MD? It's rational functions on C with poles bounded by M times D. And here just M is going to be some integer. And sorry, and it should be a function on this to the n. So meaning I'm gonna plug in for each of these xi's a rational function on C with bounded poles. So where does f send such a n tuple? Can anyone tell me? So what happens? So what are we doing? We're taking a bunch of meromorphic functions, rational functions with bounded poles. We're multiplying them together. Each term in f has degree whatever it is. It's some constant degree d because f is homogeneous. And then we're multiplying by the coefficients of f, which are also maybe some rational functions, which might have some poles. So what does that give us? It gives us a rational function with poles bounded by what?
MND or something?
Yeah, so it's O of, it's not quite n, it's O of degree f times md. Okay, but then we might get some d prime here coming from the poles of the coefficients of f. So here, this comes from the poles of the coefficients. Great. Okay, so this is some map. This is a map of affine spaces not over KC, but over K. So does everyone understand how I'm thinking of f as a map like this? Maybe actually let me move the notation f to be next to the arrow to give myself a bit more room. So does anyone have any questions about how I'm thinking of this polynomial f as a map between these two affine spaces?
Can you repeat that again?
Yeah. So all I'm doing is I'm taking these rational functions on C. So a section to O of MD is a rational function on C with some bounded poles. And then I'm just plugging them into F. That gives me another rational function on C. And I'm claiming that the poles of that new rational function are bounded by this. So in other words, in each monomial, the order of the pole can increase by up to degree of F because we're multiplying a bunch of things together. But then we have some extra poles maybe from the coefficients of our function F, which are rational function on C, so they may as well have poles. All right. Does anyone else have questions about that, or did that answer your question, Peter?
Yes, thanks.
Right. All right. So let's think about this. So what are the dimensions of these spaces? So first of all, what is the dimension of this source space? So this affine space here, or like how does it grow?
I guess it's a linear function
Yeah, so linear in what?
in n.
Yeah, that's right. So it's in fact, so this grows like m times n, right? So it's this up to some constant, right? So that's from the Riemann-Roch theorem. It says that this, before you take this n here, this grows like, it has slope 1, and it grows like m, right? So it's like m plus some constant. And then we're taking to the nth power, so that the affine space as a whole grows like m times n. All right, what about this bottom one? So how does this grow?
It's degree f times n.
Yeah, so this grows like up to an additive constant. This looks like degree of f times m. Okay, so m times m, degree of f is less than n, right? So by assumption, number is bigger. The top number here is bigger than the bottom number. Do you guys agree with that? Great, thank you, Freddie. All right, so what that means is that we have a map for m big. So for m bigger than 0, much bigger than 0, then we have a map from x to y. Let me just call this x, and let me just call this y. They're both affine spaces with the dimension of x bigger than the dimension of y, which implies that the dimension of any non-empty fiber is positive. So what are we interested in? Which fiber of this map? So we're trying to produce a 0 of f. So that's the fiber over which point of our target space, y.
Zero.
Yeah, exactly. So we want, it would suffice to show that the dimension of f inverse of 0 is positive. Well, because we're over now, this is a variety over an algebraically closed field. This is a map of affine spaces over K. So to produce a 0 of f, it's just enough to produce any point in the fiber, which just doesn't correspond to 0, 0, 0, 0, 0. So if the fiber is positive dimensional, such a point exists. And so it's enough to show that f inverse of 0, so this fiber is non-empty. Because if it is, it must be positive dimensional by the previous remark. So why is that? Why is f inverse of 0 non-empty?
F is homogeneous.
Yeah,
It's in
yeah,
0,
exactly.
0.
F is homogeneous, so that means that 0 is in f inverse of 0. So we're done. Great. I think this is an absolutely beautiful proof. It's like one of my favorite proofs in all of math. Yeah. So and you see, I mean, here we were proving something about that feels, at least to me, like this kind of statement that the function field of a curve over an algebraically closed field is quasi-algebraically closed feels like a real like kind of algebra statement, and we really use geometry. We use the Riemann-Roch theorem. I think it's really awesome.
Wait, question. Even if 0 is in the fiber, how does that imply that the dimension is positive?
Yeah, so it was this previous line. So we estimated the dimensions of these spaces. We said that for m really big, this space was bigger than this one, right? It had a positive, higher dimension. So what that tells you is that any non-empty fiber has positive dimension.
Don't we need some properties about the map F for that to be?
It's true for maps of finite type varieties over a field.
Okay.
Oh, and maybe, yeah, sorry, you need that it's, yeah, you need that it's irreducible, I guess. Yeah, but these are affine spaces. Yeah. Does that answer your question, Arvin?
Yeah, thanks.
Yeah, sorry, you're right. You do need that. I guess varieties are irreducible. So what I said is strictly speaking true. Okay, so this so the corollary is that the Brouwer group of K of C, and this is the same by this theorem of Serre that I quoted earlier. Okay, and then I'm going to say so the same is true. So the proof for K, the fraction field so let's say we have the fraction field of a strictly Henselian DBR. And the claim is that this is also quasi-algebraically closed. So think, for example, the strict Henselization of the structure. So the stalk of the structure sheaf at a curve over an algebraically closed field at a closed point. That's an example of a strictly Henselian DBR. Another example is if you take the Witt vectors of FP bar. That's another example. So this I'm not going to prove, but it's in Lang's thesis. Okay, and a good exercise. So exercise is to try this when so prove this when K is echo-characteristic 0. So that's not so hard and is similar, and the idea is fairly similar to what we just did. All right, cool. And then the corollary of this theorem, which is in Lang's thesis, and I will let you take a look if you would like, is that the Brouwer group of K is the same as H2 of K with coefficients in GM, which is 0. For K, strictly Henselian. DBR, or fraction field of one of those. All right. Are there any questions about that? All right, so now let's prove some amazing stuff using this. So let's relate this back to let's compute something of the higher cohomology of fields. So what have we done? We've now shown that for these special fields, so K of C, and assuming this result of Lang, the fraction field of a strictly Henselian DBR, H2 of GM is 0. What we did earlier is we related the Etale cohomology of curves to the cohomology of fields with coefficients in GM. And so we've done H2, now we want to do all of HI. So the theorem is, let's let K be as above. So by as above, I mean K of C or KX bar, where this is the function field of a curve over a algebraic closed field, or this is the fraction field of a strictly Henselian DBR. Then the theorem is that HI of K with coefficients in GM is 0 for all I bigger than 0. All right. So this is kind of the main theorem of the day. So let's talk about the proof. Are there any questions about the statement before we get into the proof, or like why we're doing this maybe? Because I know the sort of motivation was maybe a couple class periods ago.
Is this going to use the fact that those are those two fields, or is it going to be just an abstract property of fields that have Brauer group 0?
Yes, so you need a little bit more than Brauer group 0. What you need is that all extensions have Brauer group 0. And so that is not true for all fields with Brauer group 0, but I think I actually have to think about that for a minute. Yeah, I think that's not true. So I think it is true for quasi-algebraically closed fields, but it requires a little fact about quasi-algebraically closed fields, that extensions of such are quasi-algebraically closed. I wanted to avoid saying that. So what's not hard to see is that a finite extension of a function field over an algebraically closed field is a function field over an algebraically closed field. So in particular, in this case, it's not so hard to see that all finite extensions have trivial Brauer group. And if you know a little bit about strictly Henselian DVRs, the same is true there. Like a finite extension of such is a strictly Henselian DVR. But I again want to avoid talking about that. Yeah, so that's why I phrased it this way. But it's true as long as H1 and H2 of GM are 0 for all finite extensions. Does that answer your question, Bob?
Yes, thanks.
Yeah, great. Cool. Okay, so are there any other questions before we talk about the proof? Does anyone want maybe a 2-minute break before we dive into the proof here? All right, I'm going to unilaterally declare a 2-minute break actually, since we're, I think, at a good stopping point, and then I'm going to prove this. So does anyone have any questions about the more general strategy while we're chilling maybe? Okay, so let me remind you broadly what was happening is that we had this Weil-Divisor exact sequence, which related the cohomology of the curve to the push forward of the cohomology of the push forward of GM from the generic point. And so what we were trying to do is understand that cohomology. So that cohomology, it turned out, by the Laurier spectral sequence essentially, was related to the cohomology of GM on the generic point itself, and also the cohomology of these strictly Henselian local rings with coefficients in GM. And so now we're showing that all of those things are 0 in high degree. All right. Anyone have any comments or questions about that?
I have a question about something else.
Yeah, go ahead.
Before. So like last time we were talking about how there's a relationship between torsors and forms of T.
Yeah.
So for a torsor, it's trivial if it has a section.
Yeah.
There's something likewise you can say for a form of T. Like for a Brauer Severi, often if you have like a rational point, it's like trivial.
That's true.
So is there something general thing you can say?
Let's actually be careful about that. So you're right that that's actually something kind of special about Brauer Severis, but I'll say a little bit more about it in a second. But like, just think about it, like a vector bundle. Like a vector bundle is the same is a form of the trivial vector bundle, right? Right. It corresponds to GLN torsors, but there are plenty of vector bundles with sections or even nowhere vanishing section.
Yeah, no, I knew when I asked that question, it wasn't going to be as simple as having a section. So I was saying, but like with a vector bundle, right? If you have like rank n sections that don't simultaneously. That's true. Yeah. Then you get a.
Yeah, that's a good question. So let's quickly talk about what happens with Brauer Severis. So if you have a section there, what that tells you is that the Brauer class is trivial, and I'll say why that is in a second. But that doesn't mean that it's a trivial form of Pn. What it means is that it's a Zariski locally trivial form of Pn. So over a field, those are the thing.
I see.
But in general, it's not quite.
I guess I was thinking of the case over spec K for that one, where Zariski locally trivial is the same as trivial.
Wait, so let me say actually, let me prove that statement you made, that if you have a section, then the Brauer class is trivial. Well, you have a section to this twisted form of Pn, right? So this is the projectivization of some twisted sheaf. So what is a point on the projectivization of a sheaf give you? It gives you a subline bundle, right, or a quotient line bundle, depending on your conventions for projective space.
Right.
So now, if you have a point of the projectivization of a twisted sheaf, that gives you a sub-twisted line bundle or a quotient twisted line bundle. And we said that if you have a twisted line bundle, your Brauer class is trivial.
I see.
So that's actually a proof of that statement you gave. Yeah, I really think this twisted sheaf point of view really clarifies a lot, honestly, even with these like kind of elementary statements about Brauer groups. Yeah, so as to your general question, like how do you tell if a form is trivial? Like, is there a good criterion in terms of sections or something like this? I don't know one off the top of my head. I think it's an interesting question, and yeah, I don't see anything obvious.
Okay, thanks.
Yeah, cool. Any other questions before we prove this theorem? All right, so this is a really fun theorem also. If it's going to use some facts from group cohomology, and I'll tell you what those facts are as we use them. But if you're not super familiar with group cohomology, you should stop me and ask questions because I'm going to be using it. Like this is kind of a cool theorem. So this theorem, by the way, is more or less due to Tate. So there's a Tate. So this is maybe I'll actually attribute. So this is arguably Tate's theorem. So really Tate's theorem is a little bit kind of a more general statement in group cohomology, but I'll just give it in this case. And it's because I'm trying to avoid talking about things like Tate cohomology. But it's cool, and it comes up in class field theory. So if you've seen class field theory, or you will see class field theory in the future, then this either is familiar, well, it should be familiar, or will be familiar when you see it later. Okay, so the goal will be to prove that it's something more, namely that hi L over K GM, and I'll say what this means, equals 0 for all finite extensions L over K. Okay, so what does this mean? Well, one way of saying it is we're computing the étale cohomology of spec K étale. If L is sorry, this should be a finite separable extension. If L is a finite separable extension, that's a cover of K, and we're going to compute the check cohomology of that cover. And I guess I'm going to keep adding words until that's true. We'll do this for all finite separable Galois extensions. Okay, and that's enough because Galois extensions are cofinal in the set of all covers. All right, so in other words, what we're doing is we're computing, so this check cohomologies are the same as the group cohomology. So this is the same. This is going to be the same as hi of the Galois group of L over K with coefficients in L cross. Okay, that's if you write down what the check complex is, it's exactly computing this. All right, are there any questions about that? I think we kind of mentioned this when we talked about check cohomology, but we weren't super explicit about the isomorphism. So if anyone has a question, you should ask it. All right. So step one is actually to observe that we know this vanishing for I equals 1 and 2. Can anyone tell me why?
One is by Hilbert 90, and then 2 is by what we talked about before.
Yeah, so that's basically right. So that would be if I didn't have this L over K here, but so in this case it's that plus inflation. It's Hilbert 90. So Hilbert 90 plus Tsen's theorem plus inflation restriction. So in other words, the inflation, I'm not going to write out the short exact sequence, but there's a short exact sequence relating these cohomology groups to the cohomology of L and the cohomology of K. If you'd like, it comes from the Hochschild-Serre spectral sequence for the map absolute Galois group of L to absolute Galois group of K to Galois group of L over K. All right. Great. All right, so now we're going to do a sort of kind of classical technique in group cohomology, which is we're going to just sort of work with more and more general groups. So first of all, we're going to do the case where L over K is cyclic. So can anyone tell me how to do this one? This requires a little bit of knowledge about the cohomology of cyclic groups.
I think the cohomology is periodic
Yeah, so and it's periodic, and what's the period?
2.
Yeah, so the cohomology is 2 periodic. Cohomology of a cyclic group is 2 periodic. So we know the answer for 1 and 2. So we have 0 for 1 and 2, and now we have a 2 periodic sequence of groups. So it's 0 everywhere. For cyclic groups. Does anyone know why the cohomology of cyclic groups is 2 periodic? It's not a tautological fact. I mean, it's not at all obvious. So the reason why is that there's, so how do you compute cohomology of a group? What you need to do is you need to write down a resolution of the trivial G module Z by free G modules. So by like copies of the group ring. And the amazing fact is that there's a 2 periodic resolution of the constant of the trivial group. Trivial G module for a cyclic group, and you just write it down. I think it's like a miraculous fact. I really don't know a sort of trivial way of thinking about it. All right, any questions about that? All right, so now let's do L over K nilpotent. So does everyone know what it means for a group to be nilpotent? Does anyone want a reminder?
Yeah, could you remind us?
Yeah, so at least the key fact I'm going to use is that there's a filtration so that the associated graded pieces are cyclic. But what it really means is that if you keep taking the iterated commutators, you eventually get 0.
I'll ask a quick question.
Yeah, go ahead.
I thought that was the definition of solvable, and now I'm kind of confused about what the difference in nilpotent and solvable is.
Sorry. Yeah, so I think what I gave you is actually the definition of solvable. So I think what we're actually going to do is solvable. Yeah, so I think you're right. You're right. So what I gave, my first definition was solvable. My second definition was nilpotent. Nilpotent implies solvable, but not vice versa. Yeah, very sorry about that, Ben.
Oh, okay.
Yeah.
I should look this stuff up because I've kind of forgotten what.
Yeah, no, you caught me. I should have. Yeah. Well, but we're actually going to do solvable, but it won't matter for this case. All right, so let's do it. So does anyone have any ideas? Okay, so so let's take the first piece of our so let's let C inside of the Galois group of L over K be normal and cyclic. So this exists by the definition I gave, by the first definition I gave, which was actually the definition of solvable. So you just take the first piece of your filtration, right? So now we have a short exact sequence C to the Galois group of L over K to some quotient group G prime, when this is also solvable, because a quotient of a solvable group or a nilpotent group is solvable or nilpotent. Maybe, let me actually, I'm going to stick with nilpotent because we're actually going to use a case, which is a nilpotent case. Okay, so does anyone see what to do now? So now we've sandwiched our group between a cyclic group, which we understand well, and a nilpotent group, which is size less than this one. So we know the required statements. Well, you have to write down carefully what the statements are because the coefficients are changing slightly. But I claim we know the required statements for G prime and C. So we know it by C by part 2 and by G prime by induction. And so now this inflation restriction exact sequence gives it to us. Okay. So now we're almost done. So now let's do it for L over K general. So does anyone see what to do now? So how do you go from nilpotent groups to general groups? There's some kind of general technique in group cohomology, which is really fun. Yeah. So what are your favorite examples of nilpotent groups? Does anyone have a favorite example?
Z2?
I'm sorry?
Z2?
Z2 is a good example. So Z2 is an example of a two group, right?
Mm-hmm.
So
you can just slap together copies of it, get all sorts of nilpotent groups.
That's true, yeah. So what's true in general is that P groups are nilpotent. Does anyone know why that's true? So P group, does anyone remember this fact that a P group always has non-trivial center?
It comes from like the class equation.
Yeah, that's right. So, okay, you should review this if you don't remember this. But so a P group is nilpotent, so why is that? It's because it always has non-trivial center. And now you can just keep quotienting by the center and your quotient has a center and you keep going. So that at least shows it's solvable, which is all you need. But in fact, they're nilpotent. Yeah, so that's the idea. Yeah, I mean, you should try to also turn that sketch into a proof that they're nilpotent. It's not hard. Okay, so what this implies is that for GP inside of the Galois group of L over K, a P-silo HI of GP with coefficients, and I'm just going to write coefficients in GM, but what I mean is coefficients in this restriction of the cohomology with the restriction of these coefficients to GP. So maybe I'll actually write that. So L cross is 0. So that's by part 3. All right. So now let's consider the map from HI Galois group of L over K, L cross, to the direct sum. This is a finite direct sum because there's only finitely many primes dividing the order of the Galois group of L over K. The HI of GP, L cross. And so we know, we just proved that this is 0. So we'd win if this is injective. So can anyone tell me why that's true? So this is injective because have you guys seen this fact? All right, so there's a map from HI of the Galois group, L cross, to HI of GP with the same coefficients. This was the P-silo. Okay, and there's a map back. Right? This is called restriction. This is called co-restriction. So this is a general construction from group cohomology. If you haven't seen it, you should take a look at Castles-Froelich chapter 4. Is where I like this. And if you go back and forth, co-restriction composed of the restriction is the same as the index of P in G, which is prime to P. So this implies that this map, so that implies that restriction is injective away from prime to P torsion. Okay, so can anyone tell me now why that implies that the direct sum of all of these maps is injective?
The kernel has to be away from prime to all the prime divisors torsion.
Yeah, exactly
That's
right.
not a thing.
Yeah, so that's impossible. Cool. Okay, and now we're done. Cool. So this, I mean, by the way, I mean, so I think for many people, I suspect this might be the first time you've used the silo theorems to prove something, like that wasn't like classify all the groups of order 127 or something. I'm not, this is a very common way the silo theorems get used, the sort of kind of reduction to P groups or the reduction to cyclic groups. It's really cool, I think. Okay, and that took me way longer than I expected, but does anyone have any questions about that? So what have we proven? We've now finished proving this theorem that the Galois cohomology of these special fields with coefficients in GM is 0 for all 0. And so just to recap, what we proved we proved it for all extensions, and then this Galois cohomology is the direct limit of over all those extensions. So that's why we're done. All right. Any questions? All right, so let's get back to Etale cohomology now. So that was a long digression, but we've won a lot from it. So now remember, C is a smooth curve over an algebraically closed field. So before we showed that the cohomology of C Etale with coefficients in GM, well, first of all, I claim this is equal to the cohomology of the push forward of GM from the generic point for I bigger than 1. Okay? Can anyone tell me why this is true? Sorry, let me be a little bit more precise about what I mean by this. So this is K of C with coefficients in eta star GM.
You can use the Leray spectral sequence, and the higher derived push forwards we know in terms of the Galois cohomology of Kx.
Yeah, that's exactly right. So what we did is before, sorry, it took me some time to get the right statement there. Before we showed that HIC Etale GM is isomorphic to HIC Etale eta star GM for I bigger than 1. And that was just from the Veda divisor exact sequence, so from the divisor exact sequence. So this boiled down to some vanishing for the sheaf of divisors. So now I claim, so the claim is actually that HIC Etale with coefficients in eta star GM is isomorphic to HI of K of C with coefficients in GM. Okay, and the proof of this claim is the Leray spectral sequence. Implies that it's enough to show that Rj of eta lower star of GM equals 0 for j bigger than 0. So we talked about this when we talked about the Leray spectral sequence, but the stalks of this are the cohomology of a strictly Henselian DVR with coefficients in GM, which we just showed is 0, modulo Lang's thesis. Great. Are there any questions about that? Okay, so now we're in really good shape. Now we get that the corollary, that HI of C Etale GM, well, we just showed this is the same as HI of K of C with coefficients in GM. Okay, but that we just showed is 0 also. Right, so the proof is that this is literally combined the corollary with what I call Tate's theorem. So the vanishing of the group on the right. Are there any questions about that? Okay, and now we win. So now we proved the theorem we've been trying to prove for the last 2 days, namely that hi of C étale with coefficients in GM is what we want it to be. Can anyone remind me what that was? So, or this is, by the way, for I bigger than 1. Sorry about that. So okay, the corollary just tells us the answer for I bigger than 1. Does anyone remember what this cohomology is for I equals 0 and I equals 1?
Should be the units for I equals 0.
Yeah, so it's just the global sections of C for I equals 0 and for I equals 1. So it was GM torsors, which had another name.
XC.
Yeah, exactly, line bundles. Great. So, okay, so the I equals 0 was tautological, I equals 1 was so-called Hilbert's theorem 90, or descent for line bundles, and then I bigger than 1 was this fairly involved Weil cohomology computation. All right, so now we can actually compute the corollary. So I'm going to state it slightly differently from how I've been doing it before. So we can compute the cohomology of C étale with coefficients in mu n, where here n is prime to the characteristic of K, where I use the usual étale cohomology convention that 0 is prime to everything, which is maybe unusual. Okay, and the corollary is that this equals something, which I told you what it is before. So it equals mu n if I is 0. Sorry. It equals the n torsion in pick C if I equals 1, and it equals let me assume, well, let me just write out the answer. So it equals z mod nz for I equals 2 if C is proper and 0 otherwise. And then it equals 0 for I bigger than 2. So let me extend my brackets downward. All right, can anyone tell me how to deduce this from the previous corollary?
Use the Kummer sequence.
Yeah, this is precisely the Kummer sequence. 1 to mu n to GM to GN. And we're using this assumption on the characteristic because we want this sequence to be exact in the étale topology. Great. Okay, so this mu n is tautological. Pick Cn is also tautological. That's just the kernel of the map from pick 1 to pick 1. Okay, and then this z mod nz is saying that if we're proper, pick 0, the component group, is divisible. So we talked about this before. If we're not proper, pick itself is divisible. Okay. And that latter is an exercise to deduce from the fact that pick 0 is divisible in general. Okay, and so I want to make a remark. So a couple remarks. So the way I've stated things now is Galois equivariant. So this is a Galois equivariant description. So why is that? Well, the content maybe is that, for example, Galois acts trivially on H2, but that follows because it acts trivially on the component group of the Picard. Great. But so if you want a non-Galois equivariant description, so we said this before, pick C n torsion is just z mod nz to the 2g. Okay, so we get it. What I'm saying is if you pick a basis for the n torsion, you get a Galois action on z mod nz to the 2g, which is probably familiar to you guys. All right, cool. So maybe just a couple remarks. So this should be familiar from the situation over C. If you have a surface of genus G. Sorry. This description is if C is proper. Sorry. So if you have a surface of genus G, the cohomology with coefficients in Z mod NZ looks the same. So I think this computation, which as you can see is really involved, like it was not trivial to show these zeros are true in high degree, was maybe the first real piece of evidence that étale cohomology was a good cohomology theory. Like it looks like the situation over C. The second kind of big calculation was Arden managed to compute the étale cohomology of A2 minus the origin, which kind of topologically looks like a three sphere. Right, that's like C2 minus the origin. And so that was the other kind of really big computation that led to I think people believing that étale cohomology was like a good idea. All right, so we've now achieved our main goal. We've computed the cohomology of curves. So that was our goal for like the first bit of the course actually, and I'm pleased we got there. So next time we're going to start building more tools. So we're going to start building towards Poincare duality, cohomology with compact support, and understanding something about the cohomology of higher dimensional varieties. All right. So we have 1 minute left. Any questions?
I have one question.
Go ahead, Peter.
So can you roll up a little bit? So in the cohomology of curves, degree I equals 0, you write mu n, but I equals 2, you write z mod z instead of mu n. Is there a difference between them?
Yeah, so the difference is the Galois actions. This is sort of what I was remarking on in this remark. So these are the roots of unity. Yeah, so C is a curve over an algebraically closed field. So suppose C was actually defined over some subfield. I mean, any curve is defined over a subfield of an algebraically closed field. Then the Galois group of that subfield acts on C. And cohomology is a functor, so it acts on these groups. Mm-hmm. So what this is saying is that the action on H0 is the same as the action on the nth roots of unity. The action on H2 is the same as the action on Z mod NZ, namely trivial.
Ah, I see. Thanks.
And it's worth noting, I mean, if you put a Z mod NZ here instead of mu n, those two sheaves are isomorphic, but not Galois equivariantly, which means that you no longer get a Z mod NZ here. You'd get some interesting action if you put a Z mod NZ here. And we'll find out what that action is later in the course.
Right, thanks.
Any other questions, Ben?
So if you looked at like HI with ZL coefficients, like L-adic coefficients. So in H1, would you have like the Tate module for the Jacobian?
You'd get the well, okay. So there's a little subtlety. So you don't literally do ZL coefficients when you take L-adic cohomology. You take the inverse limit of the Z mod L to the n cohomology. So that's the definition of L-adic cohomology. And by the way, anyone should feel free to go at this point since class is over. What you'd get actually is the dual of the Tate module.
I see. So where does that?
Because it would twist the Galois action. So pick Cn is actually self-dual, not Galois equivariantly because of the Tate pairing. Right. So it's the same. It's sort of the same, but the Galois action is different. So you get this you get the Tate module twisted by -1, I think, by the dual of the cyclotonic character.
I see. I guess I'm not really seeing where the dual comes from in this description.
Yeah, so it comes. It's not so obvious. So I think from this description, what you'll get is the twist. You'll get this twisted by 1 or -1. I would have to work it out. But then that's isomorphic to the dual because of the Tate pairing.
Mm-hmm. Okay.
Yeah, it's a good question. Any other questions? All right, I'm going to stop recording that.
Bye.